Hi everyone, in this video we are going to discuss knocking. And so knocking is something that was a very, very big problem back in the early 1900s, and it was something that happened within your internal combustion reaction. So let's get a definition of knocking first before we go into the history. So knocking is essentially an unexpected, this is a very important piece of it, it's unexpected spark that ignites your fuel. Again, this is within a car, okay? So it's an unexpected spark that ignites your fuel. It's your gasoline, essentially, your fossil fuel, that causes a violent combustion reaction. So these people would be driving down the street, and all of a sudden they would hear this big crazy noise, and then they would see smoke, their engine would start to overheat, and eventually they would have unbelievable engine damage, so it would destroy their engine. And so they were trying to figure out, the scientists were trying to figure out what was going on. What is this noise? Why are our engines overheating, and why are our engines dying? What is going on? And so eventually they figured out that it has to do with the type of hydrocarbon that you use as a gasoline. And so they came up with this term called octane rating, in order to rate essentially these different types of hydrocarbons, specifically the different structures of these hydrocarbons, to say which ones of these are more likely to knock and which ones of them are not. And so an octane rating is essentially just a number that represents a specific molecule. We'll make this possessive. So a specific molecule's resistance to knocking. And so whenever you come up with a term like this, you absolutely have to have a standard. And so they arbitrarily picked isooctane. And they said, okay, let's just say isooctane has an octane rating of 100. Let's compare that to something like N-octane. So N just means normal, and it indicates that you're in a linear geometry. So let's look at N-octane. So they compared isooctane and N-octane, and they said which one of these is more likely to have that unexpected spark and have that violent, crazy, uncontrolled, that's a big part of it, combustion reaction. Well, if isooctane has a value of 100, so very resistant to knocking, N-octane has a value of -20, so not resistant to knocking at all. So definitely isooctane, it was a much better fuel source. So let me see if you can use some information here and extrapolate that to a different problem. So let's say that N-heptane, let's say N-heptane's octane rating is 0. So would you expect for isoheptane, hep 7, to have a positive or negative octane rating? Okay, so use the information we just discussed, and I want you to try to deduce something else. So pick new information. What do you think? All right, did we get an answer? Hopefully we did, and the correct answer is definitely positive. Isoheptane is an isomer of N-heptane, and it definitely has a value of 42.4 for its octane rating. And so what we can take from this is that branched molecules have a much better geometry when it comes to resisting knocking. So branched molecules are much better than their linear isomers, okay? So that's what we need to get from this. All right, so let's take it one step further, and let's actually look at oxygenated fuels. So we've kind of mentioned these before, but we haven't gone super in depth with them. But essentially an oxygenated fuel is just something that has a hydrocarbon chain. So it's not just a hydrocarbon, but it's primarily carbons and hydrogens that also have some sort of oxygen atoms in there. Now, the reason we look at oxygenated fuels is for one very main important reason, and it essentially is because it burns cleaner. So what I mean is you take these fuel sources that have oxygen in them somewhere, you treat them with O2, and they create less carbon monoxide than their non-oxygenated counterparts, okay? So they actually burn cleaner. The one downside from them is that they are definitely producing less energy per gram combusted, Okay, so the positive thing, better for the environment, they're not creating that lethal carbon monoxide, but the negative part is that they do not actually produce as much energy. But I want to look at two specifically, so very specific examples. So we're going to look at ethanol. We know ethanol because we drink it, or maybe your parents drink it based on your age. And so this is what exists in vodka. It's what is vodka essentially, and then we also put it in beer. Another source of ethanol is we use it as an alternative fuel source, and so we'll get to that later on. But another one we look at is called methyl tertiary butyl ether. So that has one carbon on this side, then it has an oxygen in the center, then it has another carbon, and each one of these carbons are attached to a methyl group, so a CH3. So essentially what you need to get from this is that each of these molecules have a bunch of hydrocarbons in there, so they have a hydrocarbon chain, but they also have an oxygen atom in there somewhere. All right, so let's get some octane ratings for this. So ethanol actually has an octane rating of 108, so it's even better than regular old isooctane. So this ethanol is less likely to knock than isooctane. And then let's look at MTBE. This one has an even better octane rating of 116 or 116. So that's awesome. I really like that. It would be super great for us if we could supplement our fuel source and add some oxygen or add some MTBE as an additive. The big problem with this is it actually creates ozone in our troposphere, and we know when we have ozone in our troposphere, it is a bad thing. It's a pollutant, it's a toxin, and so it's not good. So right now, ethanol is actually our #1 source in terms of octane ratings, especially because it's a clean fuel source. All right, take care of yourselves. Have a great week. Drink water.